So I want to talk about how engineers, the engineering sciences and the associated professions are going to engineer our future, the future of mankind. And by doing that, it will give us an idea as to what the future of the engineering sciences and the engineering professions are going to look like. Now, you might say, well, Mark, you're talking to a whole load of engineers and you want us to make us feel good and important. Well, I should say that the current Minister of State for Science and Technology, Patrick Vallance, the Lord Patrick Vallance now, when he was addressing the Institute of Mechanical Engineers on their 175th anniversary, he made it absolutely clear that there are issues of global concern that are getting more and more concerning, and he highlighted issues in healthcare, issues in the environment, and issues in security. And he said, these are global concerns, and they're getting more concerning. And there is no doubt that engineering has a major central role to play in the global challenges, whichever ones you choose to pick. And I think that that's absolutely correct, that engineering is the major, or one of the major central roles that has to be deployed in us successfully addressing some of these global challenges that we face now and in our future. And so engineers working with others will be absolutely central to this. And if I just look at some of the initiatives that are ongoing here in Cambridge, it illustrates the call to arms that we are starting to hear in terms of addressing some of these global challenges. If we look at the aviation sector and the Whittle Laboratory developing the Impact Accelerator, seeking to address the environmental impact that the aviation industry is having. And there are many others. Some of you will be familiar with the Centre for Climate Repair, the Cambridge Institute for Sustainability Leadership, and I won't read them all, but you can clearly see that even here in Cambridge, and this is replicated across the UK, and it is replicated across all of the great institutes across the world that are seeking to ensure that we as mankind are effectively addressing the challenges to us now and as we head into the future. And what I thought I would do is look at an example where engineering science has delivered the future. And it is, some of you will be very happy to hear, a big geotechnical contribution. But the implications of what has been achieved here are absolutely profound, ones that we are currently living through and are engineering our future. And that is, if the clicker works, it does. Let me get back to it. Is this here? The submarine cable capability across the whole of the world, connecting across the North Atlantic, the South Atlantic, the North and South Pacific, in the Indian Ocean, and providing the means to transmit data and information and connect the world globally. And just to be absolutely clear, the investments that are currently being made in continuing to build the capability and the capacity of this submarine cable facility is coming from the business sectors, the businesses that are having an absolutely transformative impact on us. And if I just read something from Google, Google is committed to connecting the world. Our investments in infrastructure to further improve our submarine cable network, one of the world's largest, which helps improve global connectivity, supporting users and Google Cloud customers. Our subsea cables play a starring role in this work, linking up cloud infrastructure that includes more than, and then they go on and cite a number of pretty impressive statistics in terms of the number of locations and the number of nodes. Meta, Facebook, they are planning in the next 2 years to have another 2 additional transatlantic cables. Right? So this infrastructure that was engineered over a century ago is playing an enormous role in our future. Now, this subsea cable network is delivering what we would know as the digital age. And components of the digital age, we hear about data. We hear about AI and the implications, the promise that these technologies have on health, on the environment, on our security of us as people and the places that we inhabit, and the other technologies that are starting to transform the way that we live and the way that we work. The whole cyber-physical fabric of our economies, our connected global economies, are all reliant upon this global interconnected communications network. Now, Cam said that there's going to be a session on AI, and as most of you know, I very seldom talk about AI, but for those of you that are thinking about it, then of course AI and AI technologies really are going to be transformative. But I would argue that they are built upon the infrastructure and the technologies and the theory that has come from, for example, the pioneering work that was done over a century ago on laying those cables. And this is what it looked like in 1866. There was one cable joining the UK, or Great Britain, the great imperial power of the time, with the USA, whose hegemony was starting to increase. And the motivation for laying that cable was economic. There was huge business interest in this. There was huge geopolitical drivers in laying this, again, because of the two dominant political forces globally at the time. And this was a huge undertaking. Why? Well, because it was the first time it had ever been done. Could it be done? Could it be achieved? So the first Atlantic cable that was laid from the southwest coast of Ireland to the tip of Newfoundland. This was very much a Victorian moonshot. And although, as I said, there were geopolitical forces really driving the development of this transatlantic communication cable, the business interests were significant drivers as well. But at the core of enabling and delivering it was engineering. The very first attempt in 1857 ended in failure. The strategy was that from the US and from the UK, 2 ships would start to lay the cable. The cable broke. 12 months later, there was a second attempt. Right? Again, it ended in failure. The cable broke. The third attempt was successful. The physical link was established, and the technical capability was available, such that a message from the then sovereign Queen Victoria to the President of the US was transmitted. It took 17 hours, so the bit rate was pretty low. But as a proof of principle, it was there. And this was the clear demonstration of the engineering prowess of such a challenge. However, less than 2 weeks later, the actual cable failed, and it failed because of a technical dispute between some of the chief engineers from the US companies and the UK as to the design of the cable and as to the actual nature of the way in which the information would be pumped through the cable. And so the argument that won the day was that we need high voltage so that we can accommodate the loss as the signals are transmitted, and we can still decode the messages. But those high voltages were such that in a very short period of time there was an internal failure of the cable. It then took 7 years before the fourth attempt could be made. Finance had to be secured. The politics and convincing the 2 governments that this was something that was still worthwhile, still worth investing in. And then, of course, a number of the technical challenges that had to be addressed to ensure confidence in the investors and those that were taking a stake in it had to be made. So, 1865, fourth attempt, and it was using, the shipping now had developed as well. The Great Eastern was the iron-hulled sail ship that was using other means of, new means of propulsion, which of course was Brunel's development, was being used to lay the cable. It ended in failure. So a lot of pressure on everybody involved. And another 12 months passed before the cable was laid successfully, and the capability of achieving around about 6 to 8 words per minute was established. And it was then that global communication arrived. And in the intervening century, And now, in the age that we live, we see just how absolutely important, how this has engineered our future, and the future that we are currently developing, that we are currently looking to, has all been built upon the core engineering that made this long-term project a success. So there was the first message that was actually transmitted transatlantically. What were some of the engineering contributions? The mathematics of impulse propagation in a submarine cable, as opposed to a cable that was actually in the ordinary atmosphere, had to be developed. The rates of achievable signal transmission, again in subsea cable, had to be developed. And it was the law of squares, the arrival curves of signals that were being transmitted had to be developed, and the analysis of the potential rates of data transmission had to be developed. And these predated Claude Shannon's work in the 1940s. The actual design of the cable, right, the thickness of the cable had to be optimized. How it was going to be effective and efficient in terms of transmission because of, again, things like inductive coupling, which was completely different subsea. How you would detect these signals, which were extremely weak, after the noisy transmission process. And things like the mirror galvanometer and the siphon recorder were developed. And these were precursors to the amplifiers and to the data recording systems that we know of today. The whole project also spawned international standards for the development of copper and the insulating material, standards for cable design, and for the quality control and testing, the various units of measurement, the ohm, right, the dimensions of screw threads. These all emerged because of the engineering that had to be delivered, engineering advances that had to be delivered to ensure this happened. And even the cable laying equipment, right, the differential equations that would govern the way in which cable would be laid, right, what the angles that would be laid at, what rates it could be laid at, and so on, to manage the induced strains on it. All of this was the engineering that was at the core of this, what I describe as a Victorian moonshot. And there you can see the mirror galvanometer, you can see the Great Eastern ship, the iron-hulled ship, and then, of course, the typical design of the cable. So I've just given you this as an example that engineering, the future, has huge implications. And so the work that you're doing, if you're an undergraduate student, I think there are some from school. If you're a postgraduate student, if you're a PhD student, if you're a young thrusting professor, if you're an old jaded professor, we should all just take courage and take note that engineering the future, no matter what it is, if it's trying to understand the mathematics of signal transmission, or trying to convince our politicians that these projects are worth supporting, convincing financiers that these projects are worth investing in. All of these aspects of engineering are going to have significant contributions to the future. Now, at last year's lecture, Lord Robert Mayor took a retrospective view on all that had been achieved by CSIC And the main word was measurement. And he took from Lord Kelvin the quotation, if you cannot measure anything, then you cannot improve it. And CIC was a trailblazer over the last 15 years in measuring infrastructure of all types and all shapes and all sizes. And what of the future of CSIC, and what of the future of engineering? Well, I then come to Brian, who's the current director, and he has said, looking ahead, the role of data in infrastructure has never been more significant. As we move into the information age, the digital era, the ability to extract actionable insights from the vast amounts of data generated by our infrastructure will be essential. Our goal is not merely to gather data, and that in itself is a significant step forward, but to turn that data into valuable information that drives better decision-making and project outcomes. And so, let me just reiterate what Robert introduced to his lecture last year, the Lord Kelvin First Baron of Largs. I often say, when you measure what you are speaking about and you can express it in numbers, you know something about it. But if you can't measure it, when you can't express it in numbers, your knowledge is of a meager and unsatisfactory kind. And we are now moving away, or we're moving forward from that notion of measurement to actually being able to say something about what we know of the systems, the processes that we are observing. And so, I would argue, as I have done for a number of years, is that the future of engineering is going to be data-centric. We require resilient and robust infrastructure. We need to monitor engineering systems that are hugely complex, that are hugely interconnected. And we need to be able to design under uncertainty. Now, let me say, data-centric engineering, is this a buzzword? Is this just a phrase that is going to go up the hype cycle and then come back down? We've spoken about Lord Kelvin and how he saw the importance of measuring things and numerically understanding. We can look through history. Gossett, who was one of the master brewers at Guinness Breweries, who incidentally, as most of you I'm sure, who have endured Statistics 101, will know that he was the developer of the student t-test. And the student t-test was developed essentially as a way of being able to better control the brewing process, using data to better control chemical engineering processes. Rudolf Kalman, of course, developed the filter, the state filter, which has been used just about everywhere and on just about everything one could imagine. Again, the synthesis of data with some sort of model of the process that one would wish to understand. George Box from Imperial Chemical Industries, who is often quoted as saying that all models are wrong, but some are useful. And he pioneered the whole notion of industrial manufacturing quality control, again, using data to better control the quality and the output of systems. And then, of course, Claude Shannon, in his 1946 paper on a theory of information and the transformation of communication systems, again, using data. So the key question is, data-centric engineering. Engineering has always been centered around data. What's new? Well, what's new is that the data that we now talk about goes beyond numbers, as William Thomson or the Lord Kelvin spoke about, to multiple modes of data, right? Multiple scales of data, both spatially and temporally. The way in which we can measure and instrument via whole sensor networks, right? Connected. The infrastructure for computing at a global scale has developed so much, and even now, AI technology is really driving the need for new compute infrastructure, and again, at an interconnected global scale. And then, of course, new theories, new technologies, developing new markets, introducing new models for business, and then, of course, the education of engineers and the skills that they are going to require to engineer the future. So what is new? There's a PhD student in here who is an employee of the National Air Traffic Service. He is working with us on a project that is using data from the National Air Traffic Service. And what is that data? That data isn't just numbers. This is whole paths of flights across the UK. Very complex data that has enormous amounts of information. And the driver to make air traffic control safer, more efficient, more high throughput requires the development of techniques and tools that use this kind of data to better and more safely deliver an air traffic control system and service for the UK. This is incredibly rich, it's incredibly complex, it's incredibly exciting data. We are going beyond numbers. I want to give an example of engineering the future, and this is quite a local example. So there were PhD students from Phoebe who were involved in this. And we at the Alan Turing Institute had been working with Greater London Authority on measuring air quality across the city for sort of obvious reasons. When the pandemic struck, they came to us because they needed, on a daily basis, to have measures of various quantities of interest, the compliance of social distancing when we were starting to come out of some of the lockdowns, information about points where in a particular borough that perhaps the transportation system was such that social distancing was going to be actually rather challenging to maintain. The data, we then pivoted that project. We pulled in quite a significant team, and one of the software engineers that worked on this is a Phoebe student. I don't know if he's here. The data were live video feeds from all of the traffic cameras across all of the boroughs in London. And what the team were then able to do was to use those videos, use that data to get an understanding of what was important. And what was important? How could people actually social distance? Were there areas where it was absolutely clear that social distancing was going to be compromised? What was the amount of traffic in a particular region, a particular borough? And that team worked basically round the clock every morning, delivering reports to Greater London Authority, and at the end of it, over 700 policy interventions had been made by Greater London Authority, widening pavements, closing off bus stops, and so on. An indication where data of a very complex kind has been used to the effect of engineering the safe future for the people of the various boroughs of London. There were various other types of data that were used in reporting, but GLA, at the end of it, working with the Turing and the team, will continue to make life better for all Londoners. And I think that's one of the core messages as far as engineering is concerned, is that we make life better for all. And just this year, that team who published the work were awarded the Wilkes Prize for whatever it was, Best Paper, published in the Computer Journal. So again, just showing how data and a data-centric approach to engineering solutions can have significant impact. I'm going to change the whole area and think about aviation and how data is actually transforming the way that we develop, in this case, technology on gas turbines. This was work that our teams did with Rolls-Royce and are continuing to do it. And I'm going to cut through this quite quickly. But basically, the idea here is that when an engine is being designed and an engine is being operated, what is the efficiency? What is the effective efficiency of that engine? And indeed, what are the efficiencies of the various subcomponents of the engine? Well, Rolls-Royce was really the pioneer of data-centric engineering. Way back in the 60s, their whole business model of power by the hour was driven and enabled by the fact that they were measuring, they were gathering data from their engines. And rather than selling engines, they were providing a service, power by the chargeable hour. And so here, to be able to assess the efficiency of subcomponents, what Rolls-Royce do is they fit a number of thermodynamic sensors onto various parts of the components of the engine. So this is the low pressure part of the turbine. And we're measuring, right? We're gathering data. But what do we notice? Well, we're measuring at a few points, not all over. And if we wish to understand the efficiency of that particular subcomponent of the engine, then what we require are the averaged temperatures so the stagnation and the stagnation temperatures. Now, the issue, of course, that we've got here is that we only have access to measurements at these points here. Well, we're producing data. So we can use that data to give us information about the distribution of the pressure and temperature across the whole component, so that the areas of the engine where we are not making measurements. And this was work, as I said, that we did with Rolls-Royce, who are making these measurements getting these numbers, but what they require is more data than their sensors can provide. And of course, what one can then do is use a data-centric approach using whatever you want to call it, data science, statistics, machine learning, or AI. At the end of the day, we are using data to then be able to give us far more information than the raw measurements give on their own. And we can then make inferences about both the circumferential distribution of temperature as well as the radial ones in regions where we cannot make measurements because of the fact that we just can't load an operating engine with sensors that would change the actual characteristics of that structure. And of course, that information is far richer than just the raw measurements. And this goes to the comment that Brian made in his remarks about CSIC, that we want to take the data from our sensors and use that to provide us with actionable insights that we can take action on and will improve, whether it's our design process, whether it's the way that we operate a system, or whatever. And so this here was used as a tool to improve the design process. I'm not going to go into some of the technical details. I know that there's plenty of you that would love to hear all of the technical details, but there's a number of papers that have been produced here that have all of that. The key message here is that measurement provides data, and data is providing actionable insights. And this is another example where if we have failure of our sensors, then the fact that we are using this data to infer the temperature profiles in regions where we cannot make measurements means that we have a system that is far more robust. That was just for one plane. We could do it for multiple planes in various sections of the engine. And indeed, an airline doesn't operate one gas turbine. It operates a fleet of aircraft which probably have at least one engine on them. And so the idea that we had was to then couple and say that we have a population of engines that are all producing data from various sensors. Some have been producing more data than others because they've been in service for longer. They all have a difference in their natural variability and their performance. But pulling that data together could give us even greater insights than using data from one single engine. And we took that idea, and colleagues from the Institute for Manufacturing who were working with Scania were very interested in using data that they were obtaining from certain engine parts in their vehicles to better understand how they could provide a better service, maintenance service for their customers who were operating fleets of vehicles. And of course, it provided a business opportunity for them in another service that was of value to their customers. We also worked with some colleagues who have been working at the Vattenfall wind turbine farm, where again we used this idea of taking measured data from individual assets and pulling them together and looking at what can we learn from the overall population. And it turns out that paper, that publication also won an award from the journal that it was published in. So I guess I'm trying to make the case that moving and evolving CSIC from measuring, gathering data, getting information from that data, producing actionable insights, taking those actions, potentially having new business models or levels of service. Many of you have seen this bridge. This was the 3D printed, so wire arc additive manufactured structure that in 2021 was placed over one of the canals in Amsterdam. And CSIC played a huge part in the success of this project. You're all familiar with 3D printing. It is a very important type of new manufacturing that allows us to come up with structures that are infeasible from subtractive style, and very powerful technology that is being adopted with an enormous potential. So we got involved with this project primarily because the designers of the structure had convinced the Amsterdam fathers that it would be just so cool if we could have this 3D printed structure in Amsterdam. And then, of course, the regulators came in and said, what are the structural properties of wire arc additive manufactured stainless steel? We don't know. What are the design standards that you're using? No idea. So we got pulled in at the last minute, and we brought together a team of structural engineers, of statisticians, computer scientists, metallurgists, to work on this project and to really understand from a scientific perspective, what are the properties of this type of material? What are the properties of the structures that are constructed from this type of material? And we wanted to make sure that no one was going to be litigated against if it collapsed or what have you when it was installed. And here are some very nice pictures of the Queen of the Netherlands opening up the bridge when it was officially put into actual use. In terms of engineering the future, what was the future of engineering? Well, the structural engineers had to work with statisticians and computer scientists to deliver this. And let me just give you some examples. So when the team were studying the material properties, well, in this case, the bulk properties, so the actual strength of the wire arc additively manufactured sections, they were using technologies which many of you are familiar with, digital image correlation, DIC. But what that provides us with is data of the whole strain field on the surface of the material. So not just at certain points where we would put specific gauges. So we're now getting data which corresponds to a whole field, an infinite dimensional object. Very exciting, and in fact, for this particular material, whose crystalline structure is anisotropic, then being able to measure the full strain field actually turned out to be extremely important. And again, we did the metallurgical analysis, which again was producing data and producing significant insights into the actual material properties of this new type of material, and subsequently the testing on the actual the hollow sections, the square and the circular hollow sections, again was producing data that was really quite transformative. And here's an example where we were producing data which was basically a scan of the as-printed structure. And you can see here, just the irregularities and the variability and the structure on the surface of the material. This is all data that is going to give us and gave us actionable insights. So from the specimens to the actual scans to the actual data, which we could then use to give us quantities of interest, such as what was the sort of levels of variability in the geometric components. Again, the testing provided us with data at scales that hitherto have not really been available, and the insights, scientific insights that this gives us are quite exciting. So let me move on as I'm taking a bit too much time, I think. I've only got about another 5 minutes. So we did all of the testing, and the Queen of the Netherlands opened it, and there was an uptick in Facebook and Twitter posts and people taking selfies on that bridge. But the data from the scanned structure then meant that we would have a digital representation of the as-built or as-printed structure. And that could then be used in our finite element models. Now, this then begged the question. We have a structure. We are making measurements of the geometry. We're making measurements of its deflection, the dynamics, as it is in use. And we have a digital representation which, to a greater or lesser degree, is going to allow us to study the response of that structure in a digital manner, right, by simulation. The open question that it posed to us was, how do we couple that digital representation with the data that is coming off the live structure? And how do we do it in a manner that is consistent, that is coherent, and systematic from a theoretical perspective? And so, of course, the team then set to work and developed the underlying mathematics of a finite element method that was based not on just the partial differential equations describing the deformation of the structure, but of the data that could be synthesized into it. And that work was published. It is now being used. Our Royal Society visiting fellow, Royal Academy of Engineering visiting fellow from Arup, who is the head of computational sciences at Arup, is now developing these codes for use in design and subsequent operation. But what this then leads us on to in terms of the future of engineering is another potential buzzword, which is, of course, the fact that we twin the digital with the physical, or the digital twin. When we think of digital twins, we often think of the digital representation being a faithful and perhaps almost identical replica of the actual reality. I think it's probably fair to say that digital twins are more reflected in the twinning that we saw in this 1980, whatever it was, film that Arnold Schwarzenegger and Danny DeVito starred in. The digital representation needs to represent what we need. And that doesn't mean to say that it will be identical, and it probably will never be. Again, what's new? Look, aeronautical engineers have been using little models and digital representations, so in wind tunnels to study performance of structures. In maritime engineering, wave tanks have been used. Structural engineers have been using straws for a very long time. Geotechnical engineers using centrifuges. Biomedical engineering using live models, right? Mouse models, although this is a rat, you'll notice. And, we've got to the point where our digital twins are almost, in some cases, like Samsung had some laboratories where they developed these digital avatars where you could have a conversation, an interactive conversation with these avatars. And more recently, with the explosion of technologies such as deep learning and these large language models and so on, this sort of technology is now having a really creepy impact, but a potentially really beneficial one in many cases. But digital twinning is nothing new. The ancient Greeks, they gathered data from watching the heavens and developed this antikytherium device in predicting. So data and a digital, well, in this case, a mechanical analog representation of making predictions of their ancient calendars based on astronomical data. I've mentioned Lord Kelvin. Got to mention him again. Tide prediction. The use of data from measuring the tides. And the mechanical twin that was then used by coupling that data to make predictions of the tidal motions. Incidentally, these machines, these mechanical machines, were used right up until the mid-40s and were used in planning, for example, the D-Day landings. Nothing new. Data and some mechanical device describing the reality that we want to understand. In weather forecasting, Lewis Fry Richardson came up with the idea of using the equations of Navier-Stokes in predicting and forecasting the weather. But before Fry Richardson, we were using weather balloons to make measurements of pressure, gathering data. And now, one of the big things that we are doing at the Alan Turing Institute is actually partnering with the Met Office in an attempt to deliver the next generation of weather forecasting. Given the climate crisis that we face, the forecasting technology has to be absolutely transformed, and data is at the heart of that. I'm going to close. Some of you will recognize this project that Ruchi Chowdhury from our division here in Cambridge developed. Underground farming. We developed a digital twin. We developed and deployed a digital twin of the environment within that farm. Again, coupling measurement sensors, the data it produced, with the digital representation that then allowed us to, or the farmers, to better control the environment, improve yield, and so on. You are all familiar with the Staffordshire Bridge. I'm not going to talk about it, but it's something that is still ongoing and producing data And the next phase is to exploit that data in not just monitoring the structure, but managing it and taking the operation of that forward. I'm going to close with one other example. Sea ice prediction. The British Antarctic Survey are doing extremely important work on monitoring how the ice caps, certainly in Antarctica, are changing, and using those measurements from satellite data to assess the rate at which these ice caps, these polar ice caps, are being degraded. Lots of data from satellites. And what we are able to do is use that data to generate actionable insights as to the rate at which these polar regions are actually shrinking. But some of the team here in Cambridge looked at this and said, these satellite images of these polar ice caps look eerily familiar to potholes on roads. And some of you may have seen one or two posters at the session where generative models are being used to generate actual images and actual trajectories of how components of road surfaces will change and degrade over time. So, let me now conclude by saying, this is another example, but I won't go into it. This is really cool, actually, with the British Antarctic Survey. And this is another one in biomedical engineering, where we are working with St. Thomas's Hospital, again on coupling data with digital representations. I started off by making the case that as engineers, we are engineering the future. And Lord Patrick Vallance has made the case that engineering is absolutely central and at the core to engineer the future, a safe, a secure, a healthy, a prosperous future for mankind. And I've then kind of moved from that to, well, what is the future of engineering? And I've made a case that the future of engineering is certainly going to be reliant on data. It's going to be reliant on taking that data and producing information that's of use and of relevance and of importance. And it's those skills that we as engineers need to develop in our workforces and in those that we are currently training. So let me conclude by saying I think the future in biomedical engineering, data will be at the core of it, and in manufacturing, design, construction, data will be at the core of it. And so I'll close there.